Welcome to the first episode of our Machine Learning by Example series. In this video, we'll walk through a simple and intuitive algorithm called K-nearest neighbors, or KNN, and use it to make predictions on a real dataset. By the end of this lesson, you'll understand how KNN works, how to train it in Python, and how to experiment with different model settings. To follow along, all you need is basic Python knowledge in either Anaconda or Google Colab. I've placed links in the description to help you set up your environment, as well as links to the dataset, the notebook for this video, and the documentation for all the libraries we'll use. Let's begin by importing our first dataset, the car stopping distance dataset. To load the dataset, we import the Pandas library, one of the most widely used tools for data analysis in Python. We abbreviate it as PD and use the read.csv function to read the data file, since it's in CSV format. Use the tab key to get auto-completion suggestions. After loading it into a variable called data, we display the first few rows using head. This gives us a quick sense of what we are working with. This dataset records how far a vehicle travels after its brakes are fully applied, given the speed at which it was moving. Our task is to build a model that takes the vehicle's speed as input and predicts the stopping distance. This is a regression problem because the output we want to predict is a continuous number. Next, let's visualize the data. We'll create a scatter plot with speed on the x-axis and stopping distance on the y-axis. For this, we import Matplotlibs.pyplot as PLT. We set the input variable, speed, to x, and the target variable, distance, to y, and then call the scatter function to plot them. At first, the plot appears without labels. So we add x and y-axis labels and call PLT show to display it cleanly. From the plot, you can see a clear positive relationship. The faster the vehicle is moving, the longer it takes to stop. However, the points don't lie perfectly along a straight line. They're scattered, meaning the data contains noise variations due to random or unknown factors. Now that we understand the data, let's introduce the KNN method. KNN predicts the output for a new point by looking at the closest points in the dataset, its nearest neighbors, and averaging their values. To illustrate this, imagine we want to predict the stopping distance for a vehicle moving at 33.5 miles per hour. If we choose 5 neighbors, we look for the 5 recorded speeds closest to 33.5 miles per hour. Take their corresponding stopping distances and compute their average. This gives us an estimated stopping distance of about 110.88 feet. Of course, manually calculating neighbors isn't practical for real problems, so we use the KNN regressor from Scikit-Learn. We import KNeighbors regressor and create a model with 5 neighbors. Training the model is as simple as calling fit. This step teaches the model the patterns in our data. Once the model is trained, we can use it to predict the stopping distance for 33.5 miles per hour. The result matches our earlier manual calculation. You may see a harmless warning about feature names. You can ignore it for now. The KNN regressor also allows us to specify how the neighbors are weighted. The default setting, uniform, gives each neighbor equal importance. The alternative, distance, gives more weight to neighbors that are closer to the input point. Using distance-based weighting, the predicted stopping distance for 33.5 miles per hour increases slightly to about 112.02 feet. Next, we use the model to predict the stopping distances for all speeds in the training data and plot the predicted curve alongside the actual data. With 5 neighbors and uniform weights, the model is fairly smooth and not overly sensitive to noise. To explore how different choices of neighbors and weighting affect the model, we wrap our plotting code into a function that takes k and w as arguments. For example, using 10 neighbors and distance weighting produces a curve with more noticeable sensitivity to the noisy points in the dataset. To make experimentation easier and more interactive, we use the interact function from IPyWidgets. This creates sliders and dropdowns that allow us to change the number of neighbors and the weighting scheme in real time and immediately see how the fitted curve changes. You'll notice that when k is very small, like 1, the model becomes extremely sensitive to noise and overfits the data. On the other hand, If K is too large, the model becomes overly smooth and loses important patterns. In the extreme case, where K includes the entire dataset, the model simply predicts the overall mean for every input. Unfortunately, there isn't one universally best value of K. The ideal choice depends on the dataset. A systematic way to choose K is to use cross-validation, which we'll cover in the next video.